After a brief idea of gamma decay process, today we are going to see an introduction regarding a very important phenomena which takes place during the gamma decay process. And this important phenomenon which also takes place when gamma decay takes place, that is called actually internal conversion. In fact, when a nucleus is in an excited state, then the nucleus get rid of the excited state by emitting energy, and this process is not uh, only by the gamma decay process, but there are several processes, there are several ways uh, following which the nucleus get rid of the excited state. In fact, when the when an excited nucleus returns back to an returns back to a state of lower energy, then not only gamma decay process takes place, but at the same time there may be other ways of decay. And among all those other ways of decay, this internal conversion is also a very important phenomenon. In fact, what type of decay will take place when the nucleus is in an excited state, that actually depends on the excitation energy. It means the energy of the nucleus above the ground state, that determines what type of decay process will take place. In fact, when the excitation energy is low, in that condition, the main processes of getting rid from the excited state of the nucleus, the two processes takes place. First one is called gamma emission and the another is internal conversion. So remember, this gamma decay and internal conversion will take place only when the excitation energy is low, not very high. Okay? And if this excitation energy is very large, let us say it is greater than 1 mega electron volt, then it is seen that apart from the gamma emission and internal conversion, the nucleus also suffer another phenomenon of decay, and that is actually called internal pair production. But in this lecture, our aim is to just introduce you to the process of internal conversion. So one thing you should remember, that in this lecture you will get only an overview of this very important phenomenon, internal conversion. The detailed analysis of this process we will discuss in the forthcoming lecture. This lecture is only aimed to introduce you regarding this process. So in fact, when the nucleus returns back to an excited state to some lower energy state, you know that energy is emitted, and that energy emitted appears in the form of gamma photon, and at the same time in some of the cases the emitted energy or the emitted energy is not does not appear in the form of gamma photon, but that energy is actually absorbed by some atomic electron by the electromagnetic interaction. So what happens in this case? The nucleus comes back from excited state to some lower energy state, and the energy is released, and the released energy is actually absorbed by some atomic electrons, and that atomic electron after gaining the energy due to the transition of nucleus from higher energy state to lower energy state may be ejected from the atomic shell in which the electron was before absorption of energy. And actually the electron will be ejected or not, that depends completely on the value of the binding energy of the electron in which the electron was present before the absorption of energy. So to understand this concept, let us consider the two energy levels of a nucleus. I have shown here that this horizontal line represents the upper energy level, and corresponding to this upper energy level the energy is EU, and this lower horizontal line represents the lower energy level, and the energy corresponding to this state of nucleus is EL. And now consider that the nucleus suffers a transition from this upper level to the lower level. In that condition, you know, the energy equal to difference of EU and EL will be emitted. Okay, so, and that is actually the excitation energy, you can say. If the nucleus is present in the lower energy level and your aim is to excite the nucleus to the upper energy level, then this much energy, that is EU minus EL energy, will be required. So EU minus EL, which I have assumed equal to W, that is simply called the excitation energy. Okay, and so when the transition will take place from the upper energy level to the lower energy level of the nucleus, then this much energy, that is EU minus EL energy, will be emitted. And now this energy W, as you have seen, is absorbed by an atomic electron. Okay, and after getting this energy, what will happen to that electron? That actually completely depends on the binding energy of the electron in the cell in which it was present. So let us consider that our atomic electron is in a particular cell, and in that cell the binding energy of that electron is, let us say, B. Okay, when you say that binding energy of the nucleus is B in a particular cell, what does it mean? It means at least you have to supply energy B from outside, and then the electron will be ejected. Okay, so definitely the ejection of electron will take place only when W will be greater or equal to B. Equal, you can say equal to. When W will be equal to B, then electron will be just ejected. But when W will be greater than B, then the electron will be ejected with some kinetic energy. Okay, it is obvious. Let us consider that the binding energy of the electron is, let us say, minus 10 electron volt, and the value of W, minus 10 electron volt, is the energy of the electron in the cell. Then binding energy will be plus 10 electron volt. So if the binding energy of the electron is 10 electron volt, and then the electron gains energy from outside which is equal to just 10 electron volt, then electron will be ejected, but its kinetic energy will be 0. But if, let us say, that it gains energy 12 electron volt, it means the value of W is 12 electron volt, then the extra energy, that is 12 minus 10, that is 2 electron volt, will appear as kinetic energy of the electron. So we simply say that the kinetic energy of the ejected electron E is equal to W minus B. Now you know that the value of this binding energy B will depend on the cell in which the electron was present before absorbing this energy. So corresponding to different atomic cell, this kinetic energy will be different. You can see, if we consider that Bk is the binding energy corresponding to the K cell, Bl is the binding energy corresponding to L cell, and Bm is the binding energy corresponding to the M cell. then the when the electron of K cell, L cell and Bm cell will and M cell will be ejected after internal conversion, then what will be the kinetic energy? You can say if the ejection of electron takes place from the K cell, then the kinetic energy E will be equal to W minus Bk. Okay. And if the electron of L cell will be ejected after internal conversion, then kinetic energy of that electron will be equal to W minus Bl. And similarly, if the ejection takes place from M cell, then the kinetic energy will be W minus Bm. Actually, as I have told you that this Bk, Bl and Bm, these are actually the binding energy of an electron present in the K cell, L cell and M cell. Okay. Now you know this binding energy actually depends on the fact that how much the electron is bonded to the nucleus. As in case of heavy atoms, the number of protons in the nucleus is very large. So the electrons of the inner cells like K cell and L cell will be much tightly bonded. If the atom is heavy, then the number of protons in the nucleus will be very large. It means Z will be large, and if Z is large, the electrons of the K cell and L cell, which is actually closer to the nucleus, will be very tightly bonded. And if those electrons are tightly bonded, what does it mean? It means the binding energy of the electron present in the K cell and L cell will be very large. Okay. If the atom is heavy, then this Bk and Bl will be very large. And if Bk and Bl is very large, then the excitation energy W, which is absorbed by the electron during the internal conversion or during the transition of nucleus from higher energy level to lower energy level, will be not sufficient to break the bond of that electron to eject the electron. Why? Because in this condition, if Bk and Bl are very large, we can see that this Bk and Bl will be smaller than W. And if Bk and Bl will be greater than W, not smaller. So in this case, this E will be actually equal to negative. You can see here, if Bk is greater than W, W minus Bk will be negative. And similarly, if Bl is also greater than W, then E will again negative. But you know that kinetic energy is never negative. It is half mv square, and so it cannot be negative. So if you see that the value of kinetic energy will be negative in case of the very heavy atom, what does it mean? Physically, it means those electrons will be not ejected. It means, so I have mentioned it here, that it means electrons of the K and L cell are not ejected if the atoms are very heavy. Okay, I think you have understood. This is a very simple concept, that the electron of K and L cell will be not ejected after gaining the excitation energy W, because the binding energy of these electron will be greater than the excitation energy W, and so in this condition kinetic energy will be negative, which is not possible, which is an absurd result. So that means that the electron of K and L cell are not ejected if the atoms are very heavy. Okay. Now just as an information, I am giving you in this introduction why this internal conversion actually takes place. In fact, you know that the electrons of an atom are revolving in an electric and magnetic field. In fact, the electric field is produced by the nucleus, and due to the motion of the nucleons, a magnetic field is also produced. So simply we say that our electron in an atom is moving under an electric and magnetic field. Okay, but due to the abrupt change in distribution of electric charge and magnetic moment within the nucleus, there will be just a perturbation. Just I have mentioned it here. You can see that semi-classically the internal conversion is due to sudden perturbation of the electric and magnetic field in which the atomic electrons move because of an abrupt change in the distribution of electric charge and magnetic moment. It means the electron, is moving in the electric and magnetic field, and here due to the internal conversion there is an abrupt change in that electric field and magnetic field, and so this internal conversion takes place. This is just a semi-classical theory. This I am giving you only an overview. The complete mathematical calculation and the real situation will be discussed in the forthcoming lecture. Okay. Now, what informations you will get after this internal conversion? When the internal conversion phenomenon will take place, what informations we get from this important phenomenon? Let us see it here. In fact, this internal conversion phenomenon gives information regarding the spin and parity of the excited states. You can gather the information of the spin and parity of the excited state from this phenomenon of internal conversion. In fact, it is seen that the conversion electrons, that is the electrons which get ejected, carry away the spins and the parity changes of the nuclear state. It means when the nuclear state changes from higher energy state, a nucleus comes back to a lower energy state, then there will be a change in the total angular momentum, that is a spin of the nucleus, and there will be also a change in parity, and that change in spin and parity are carried by the conversion electron, by the ejected electrons. Okay, but this internal conversion phenomenon does not give only information regarding the spin and parity of the spin and parity changes of the nuclear state, but it also gives information a little bit, you can say a little bit information about the structure of the nucleus. From the idea of internal conversion, you can deal with the structure of nucleus to some extent. Okay. In fact, all these informations which we gather from the internal conversion phenomenon, that is the parity change or the spin change or the structure of nucleus, all these informations we get from the study of a very important parameter, very important quantity in this internal conversion phenomenon, and that very important quantity in terms of which we get the information regarding the parity and spin changes, structure of nucleus. These are obtained from the study of a very important quantity, and that quantity is called internal conversion coefficient, and we denote this internal conversion coefficient by the symbol alpha. It means you can calculate the value of the spin change, parity change, or you can know about the structure of the nucleus by this important phenomenon, internal conversion, in terms of the quantity which is called internal conversion coefficient. So now I will give you a basic idea of this internal conversion coefficient and in this lecture, but in the forthcoming lecture our prime aim will be actually the calculation of this internal conversion coefficient. But in this present lecture, as I have told you that this is just an introduction regarding this phenomenon internal conversion, I am giving you just the basic definition of this internal conversion coefficient. Okay. In fact, you know that when the nucleus returns back from an excited state to some lower energy state, then uh, the internal conversion takes place. The emitted energy is actually absorbed by the atomic electron. But at the same time, you know, gamma decay also takes place. Not only these two, but there are so many decay processes like beta decay, so many decay processes in this condition takes place. Okay. But here we will consider only two processes. First one is internal conversion and the second one is gamma decay. So let us consider that that a nucleus transits from a higher energy state to a lower energy state, and in that transition there is a gamma decay process and also an internal conversion process. What does it mean? It means there will be an emission of electron, atomic electron, and at the same time there will be also the emission of gamma photon. Okay. In fact, this internal conversion coefficient is defined as a ratio of the number of conversion electron emitted to the number of gamma photons emitted in the same time interval. Okay. If you consider that in a particular given time interval, the number of ejected electron is equal to Ne and the number of ejected photons is N gamma in the same time interval, then when you will divide the number of ejected electron by the number of ejected photon, then that ratio is called actually the internal conversion coefficient. So alpha is defined as Ne over N gamma, where Ne is what? As I have told you that Ne is simply the number of conversion electrons emitted, and N gamma is number of gamma photons emitted in the same time interval. Okay. This is the basic definition of internal conversion coefficient alpha. Okay. Now actually this alpha is related to the decay constant for the decay of gamma and decay of the electron. Okay, it is clear. But so we can also define this alpha in terms of the decay constant. Let us see how we can define this alpha in terms of decay constant. In fact, you can consider that this lambda gamma. Let us consider that this lambda gamma is the decay constant representing the probability per unit time for the emission of gamma photon. You know, lambda, which is decay constant, that is actually the measurement of probability, rate of probability you can say, or probability per unit time you can say, for the emission of gamma photon. And similarly, we will also consider that the decay constant lambda E represents the probability per unit time for the internal conversion of electron. Okay. As I have told you earlier that not only the gamma decay process and the internal conversion process takes place when there is a nuclear transition from higher energy level to lower energy level, but at the same time there are other processes. You have seen that there may be a pair production, there may be beta decay and so on. But in the concept of this internal conversion coefficient, we are considering that only two processes take place. We consider it. The first one is the internal conversion and the another is the gamma decay. So if we neglect all other decay processes and consider that only these two processes takes place, in that condition the total transition probability, or you can say the total decay constant lambda, will be what? That will be lambda gamma plus lambda E. Okay. So the total transition probability, if these two processes only takes place, that will be given by lambda equal to lambda gamma plus lambda E. And if you can take this lambda gamma as a common factor, then what will be your result? Then lambda will be equal to lambda gamma times 1 plus lambda E by lambda gamma. Okay. Now, from the definition of this internal conversion coefficient alpha, you have seen that this alpha is equal to Ne over N gamma. But Ne is the number of ejected conversion electron and N gamma is the number of ejected photon, and this ratio will be simply equal to the ratio of the decay constant for the internal conversion and for the gamma decay. So Ne over N gamma, this is simply equal to lambda E by lambda gamma. Okay. So you can also define this alpha in this manner, that this is just the ratio of probability per unit time for the internal conversion and the probability representing the probability per unit time representing the gamma decay. So alpha is also defined as lambda E by lambda gamma. And as alpha is lambda E by lambda gamma, you can substitute here in this equation 2 at the place of lambda E by lambda gamma alpha. So what will be lambda? Lambda will be equal to lambda gamma times 1 plus alpha. Okay. Now this alpha for a particular nucleus is almost constant. So it is obvious that if alpha is constant, you can see that this Ne will be equal to alpha into N gamma. Okay, N gamma. And so we can say that this Ne will be proportional to N gamma. So simply we can say that Ne is proportional to N gamma. It means when the number of conversion electron will be large, then definitely the number of ejected photon will be also large. It means when gamma decay, the probability of gamma decay increases, at the same time the probability of this internal conversion also increases. So this was actually a brief introduction regarding this internal conversion process, but in our forthcoming lecture, our prime aim will be actually the calculation or determination of this internal conversion coefficient alpha, and that is done in terms of the concept of retarded potential. Not actually the problem can be dealt in terms of the quantum electrodynamics, but that will be a rigorous process, a tough process. So we will actually follow the concept of retarded potential for the determination of this internal conversion coefficient alpha. So in forthcoming lecture, our lecture will be concentrated for the calculation, for the computation of this alpha.